In this section, we're going to learn about the momentum of a photon and the Compton shift. Now, you might be wondering, well, how can a photon have momentum? After all, a photon has no mass. And isn't the formula for momentum mass times velocity? Well, before we consider what the actual formula is, let's remember that even in classical electrodynamics, an electromagnetic wave can impart momentum to an object. So therefore, we have to have a broader definition of momentum than what we have used in mechanics. Now, this is our classical formula for the momentum. The momentum is equal to the mass times velocity. But because we are dealing with light, we have to use the results of special relativity to define the momentum instead of this simple formula. So we will use this equation from special relativity that says that the energy of a particle squared is equal to the momentum of the particle times the speed of light, the quantity squared, plus the rest mass of the particle times the speed of light squared, the quantity squared. Now, a photon has no rest mass, and so therefore its energy would simply be equal to its momentum times the speed of light. Solving that for momentum, we see the momentum is equal to the energy divided by the speed of light. And if we substitute in Planck's formula for the energy of a photon, we find that the momentum is equal to h over lambda. Because as you know, the frequency of a wave times the wavelength of the wave is going to equal the speed of that wave. And substituting that in gives us this formula. For an example of the effects of a photon's momentum, let's take a look at what's known as the Compton shift. So if a photon is a particle with energy, it also has momentum. And as we have just seen, the momentum of the photon is given by the formula momentum is equal to h over lambda. So if a photon collides with an electron, it can gain or lose momentum as the electron gains or loses momentum, because momentum should still be conserved in that collision. So if the momentum of the photon changes, that means its wavelength is going to change. This is known as the Compton effect. Here's an example of the Compton effect, or so-called Compton shift. I'm not going to actually ask you to solve this one. I'm just going to leave it here if you decide that you want to go ahead and solve it, because the Compton shift is not even on the AP exam, even in normal years. Here is the solution to that Compton shift problem, if you're interested. And here is a two-dimensional Compton shift problem. All you're using here is conservation of momentum and the formula for the momentum of a photon. Here's one that you should be able to answer without doing any calculations. We'll take a look at this. In a Compton scattering experiment, the incoming photon travels in along the x-axis and scatters in the negative x direction as shown. Which vector best describes the direction of the recoil electron's motion after the collision? Is it A, B, C, or D? Well, I think it's pretty clear from conservation of momentum that if the change in momentum of the photon is in the negative x direction, the change in momentum of the electron must be in the positive x direction. Now, the Compton effect is not usually noticed with visible light because the size of the shift is small compared to the wavelength of light. But X-rays have much shorter wavelengths, so we will notice this shift happening when an X-ray photon collides with an electron. So what we've seen in discussing the Compton shift and black body radiation and the photoelectric effect is that there seems to be a duality in the nature of light. In some experiments, such as those I just described, the light behaves as a particle, which we call a photon. In other experiments, like double-slit interference and thin film interference, we explain the behavior of light as a wave. Light never appears to be both in the same experiment. The famous physicist William Bragg said, "God runs electromagnetics by wave theory on Monday, Wednesday, and Friday, and the devil runs them by quantum theory on Tuesday, Thursday, and Saturday."